So I'd just like to mention, in case it's not obvious already, that this seminar can be disorganized at times, more specifically every Thursday. And it's disorganized and, well, just not very systematic. It's very example-driven, and I don't know exactly what audience level to pitch to. And I'm sort of feeling around, and sometimes going high, sometimes going too high, sometimes going too low. And it just really helps if I can get, feedback from people, I guess both during class and after class. I'm still a lot outside of the seminar if people want to ask questions about it.
More theorems.
More theorems. Oh, well. All right, that's done.
There are theorems, you just have to find them, right? He's proving tons of theorems. They just don't all start out by saying theorem.
So, right now I'm continuing with an example that I talked about last Thursday, which is sort of using the Gram-Schmidt process, sort of in a categorified way, to find the irreducible representations of the group. In this particular case, of the group of 4 permutations of 4 elements. And basically what we got to last time was we drew the matrix of an inner product that we're going to use in the Gram-Schmidt process. And I guess the most important thing about this matrix is I have to remember, were we listing the Young diagrams in order from vertical to horizontal or horizontal to vertical when we were
Vertical to horizontal.
on the left we have the vertical one, and on the right we have the horizontal one.
Yeah, starting at the top you have the vertical.
Oh,
Okay.
yeah.
But you also said that you wanted to reverse the order eventually.
I did.
Maybe
Yeah, you did it the wrong way.
I did the wrong one.
Maybe you're starting here.
Oh, okay. All right, so we're going
I'm in the
to try to get it right.
Yeah.
Yeah. Now, where's there's one sort of edge of the matrix that has a lot of ones in it. It's like very trivial. Is that going to be the
First row, first column.
Okay. Because we're counting, these ones are counting the number of ways that a thing of some kind can relate to really to nothing at all. It's one way that can relate to nothing. Over here, we're really counting the number of ways that can relate to everything. So we're really counting the separate numbers of things. So there's 4 elements. There's 4 elements of 4 elements. There's 6 ways of splitting 4 elements apart in half. There's 12 ordered pairs. I guess these are unordered pairs and then these are ordered pairs. Yeah.
Non-degenerate.
Non-degenerate ordered pairs, right? And these are complete listings of everything. What numbers do we have here? 2? I'm sort of trying to do this by numbers. Can you remember the numbers?
There's 3's at the diagonal.
3's where?
Right up, yeah, up the.
All
up
of
there.
it?
3.
Like that?
Yeah.
And 4 is there?
4 is there.
That's okay. Okay. So this has sort of two interpretations, a categorified interpretation and a decategorified interpretation. The categorified interpretation is that counting Hecke operators for us. It's counting the size of a Hom space between permutation representations. Each one of these numbers is doing that job. And the decategorified interpretation is that this whole Hom functor, when decategorified, is just an inner product to which we can apply the Gram-Schmidt process. So, how does the Gram-Schmidt process work? You start out with your first vector in your basis. So again, Gram-Schmidt is supposed to sort of take an ugly basis and turn it into a prettier basis. And what's ugly about the basis that we're starting out with is that this is not an orthonormal basis. The inner product doesn't look just like a Kronecker delta matrix. It doesn't look like a Kronecker delta matrix. So, so we're trying to prettify the basis, get a better basis that's orthonormal. And we start out by taking the first vector in our list, and we just keep that. So how do we write this down? I guess what we should do is, you sometimes think of the Gram-Schmidt process as, well, we're creating a new basis. We started with an old basis, creating a new basis. So we have a change of basis, and that change of basis is itself represented by a matrix. And in fact, it will also be an inverse change of basis matrix. And we want to keep track of one or both of those. So let's make a new matrix here. It'll be the change of basis matrix. Ready? 1, 2, 3, 4, 5. So I'm going to put the old basis up here. I'm going to put the new basis up here. And both bases are indexed by the same set, namely the set of these Young diagrams. So it's one of our sort of double meanings of Young diagrams. Over here, the Young diagrams are symbols for certain permutation representations, namely permutation representations of the group acting on flags on the set. So it's flag representations. And the new meaning of the Young diagrams is they'll be standing for certain irreducible representations. Representations in our new basis for the representation category. So, yeah, do the same thing. Same symbols, different meanings. Okay. So, yeah, so we're creating the new one list one by one. So we're going to sort of create this matrix row by row. Right? Each row is going to tell us what the new replacement element is for the old base element. And the new one will be some mixture of the old ones. So that's what we're doing, row by row. So, can anybody tell me what the general rough shape of this change of basis matrix will be? On base of what I just said?
Sort of triangle.
Somebody just said, yeah, it's going to be a triangular matrix. Can somebody tell me whether it's upper triangular or lower triangular? I think it should be lower triangular, yeah. In fact, sometimes the top row. I've already announced that we're just going to keep the first one. Okay. And then, as we go down the list, this one will be a mixture of these two. This one will be a mixture of these three. So it's going to be lower triangular link. So. Okay, exactly. Where do we go?
6, 1, 3 plus 6.
Okay. So, let's see. Okay, and there's another thing that's, I think there's another little bit that's going to help us here. I think I've already mentioned this.
The diagonal entry.
Yes, the diagonal entry. And why is that going to be so easy for us? It's a little bit of magic that I don't completely understand. In general, the Gram-Schmidt process can involve, it produces an orthonormal basis. So one of its jobs is to normalize things. And normalizing could be multiple. The normalization part could really involve having factors here that aren't just one. But for some strange reason, in our example, we're never going to have to actually really normalize. Things are going to sort of automatically become normalized for us. And I guess this is sort of expressed by the idea that John said that inside of each one of these fat representations, there's a skinny representation trying to get out. There's just one skinny one that's trying to get out. There's some other garbage in there, but it's sort of the extra garbage that we're trying to get out. But so there's a unique copy of this irreducible in this flag representation. There's a unique copy of this irreducible in this flag representation. Is that for some mysterious reason?
And that's why we give them those names.
What?
That's why we assign them the same names.
That's right. That's right.
So he is in representation theoretic.
Yeah.
We give us this fat representation, and of course, it's a direct sum of all these garbage ones with skinny ones. How do you identify that skinny one?
That's a very good question, and the reason I'm not going to answer it is because that's a very categorified question. In other words, what we're going to be doing a sort of very bad job of this thing. We're going to do a very decategorified job, and we're going to just. One way you could describe this decategorified attitude that we're taking is you could say that we're just working at the level of the characters of the representation.
Yes.
And in other words, you can just like add and subtract, formally add and subtract representations from each other or their characters, and you don't even, when you're taking this attitude, you don't really see the actual copy of the representation.
Exactly. Yes, I want to see that copy.
Yes, we do want to do that. We want to see that copy, but not today. We're going to.
Someday.
Yes, yes. That's a big goal is to revisit this calculation later from a categorified point. But I'm starting out doing it at the decategorified level. Perhaps one reason is because the decategorified level is sort of easy because it ignores all the hard work. But in some sense, it's not just easy; it's also powerful because you can get away with ignoring the hard work. So each different level that you can work on, categorified level or the decategorified level, has its own advantages. One's more explicit, one's easier, and there's a sort of trade-off there. But there's also a sort of cooperation there. That, you can do part of the work one day, and the other part of the work the other day. Okay, we kind of got our first non-trivial entry in the matrix here. So, what are we supposed to do? We're supposed to, how do we get, so, okay, right, so the problem is that this representation is not orthogonal to this representation. We have to repair it so that this new representation will be orthogonal to this representation. So, how do we perform that calculation? So over here, let's check to make sure, to demonstrate that this representation is not orthogonal to this representation. So how do you do that? You just look at the matrix entry and you see that it's non-zero. So that's bad, and that's bad. That's sort of telling us how bad it is. So it's telling us how much we have to sort of fix it by.
So -1 should be there.
Yes, we have to subtract one copy. Like that. And
Incidentally, does the dot cosmos correspond to the one-dimensional representation?
so it is.
That copy, is that the...
Yeah, you can tell if you think that if you think that it's a permutation representation, it already is a trivial representation. It's the group acting on the one element set. Yeah, so it is. Yeah, so that's sort of tip off. That's a good place to start. It's the only. Yeah, so this is the only. In a sense, this is the only place you can start if you want the process to work smoothly, because this is the only one that sort of has a foot in both worlds. It's both a flag representation, a permutation representation, and an irreducible. So, I guess I'm kind of hoping that somebody is better mechanics of the Gram-Schmidt process than I am. What are we supposed to do now? We're supposed to take this representation and do what?
The inner product of the third and first. Copy of the first one.
Okay, right. So we compare it to the first one, and
Yeah, and to subtract one, we can put a -1 on the first column again. You can put a -1 in every other entry in the first column.
But you now have.
you start repeating.
Because the first one is already part of your basis.
Yes.
No, but it's not that simple because
It's not, yeah.
you
Because you have-
subtract it.
Oh, yeah, yeah.
You're gonna be now.
Well,
I really need to.
Maybe we have
Yeah,
to
but
You're correct, right.
Okay, so we better go row by row. We better think about it row by row. And okay, so what are we trying to do? Are we trying to fill in, I guess, this first and then this? Is that where we were?
We're trying to film it at the same time. You know,
Fill in at the same time.
you can. You have to do one for the other first.
Yeah.
And then you see. So you replace your old third representation by the old one minus some of the first one, say.
Yeah.
And then you see what the inner product of that is with the second one, and then you subtract off that much of the second one.
Am I writing enough on the board? Should we be doing this in our heads? Should we just be filling this in? Or is there something I'm not writing that I should be writing down?
I think that everyone else should just start working harder. Stop just sitting there and start telling
You
you.
tell me the numbers?
Yeah,
Really? You're making it sound like,
it's easy enough to do. They just got to do it.
okay. I'd like to see it systematically.
Maybe it's
I'd like to algorithm
we
right down
can't
the
put
board.
-1 in that entry.
But then modify it up.
And then modify this, and that'll help us get the next entry in that row. So kind of like, it's almost kind of like we're going to guess at the -1, see what it does in the next row.
It's not a matter
I don't
of,
get a guess.
you don't need to
You're
guess
right,
in
but-
Gram-Schmidt.
Yeah. No, it's not -1.
Right.
But you have to start that way.
That's too much more systematic way.
But then you write down the equation. That's the...
No, you don't need to write down. Well, you can if you want, but you can be perfectly systematic and do it in your head, right? So it's not that hard to do Gram-Schmidt in your head.
Well, I have a trouble figuring out what to do the next time. What should I do?
I think you should really not subtract off some of the first one from the third one. You should subtract off some of the second one from the third one.
What's
my
the second
theory.
one? You mean this one or this second one? The second old one?
The second old one, right? Because
We
we're
have to work with the old ones first.
Okay.
So what he's saying is we should really start with,
Yeah.
we should really start with the entry,
This is it, yeah.
the 3Q entry right here. We should really find this one first.
Yeah, yeah. Okay, this is correct. And the way you do it is as follows. You subtract, what is the entry there? It's 2. The 3Q entry is 2.
Yeah.
Yeah. So that means you want to subtract 2 from there. You want to write a -2 there?
Okay.
I think so. Then you want to write a +2 there?
Plus 2 where again?
Yes. Because shouldn't that be what the second row?
Okay.
And now you want to subtract the 1. Now you want to subtract the 1, so that becomes a 1. So it should be 1 minus 2, 1. This my guess. Somebody tells me it's 9 minutes.
Yeah. I think chemistry that tells.
I'm just the
Two
camera
and
man.
minus 2, that's subtracting 2 copies of the new second representation.
All right, so 1, negative 2.
That's negative 2.
I'm
That
sorry.
means subtracting 2 of the old.
2 of the old, but what is 2 of the old in the new set? They are twice minus 1 and 1. So I'm subtracting 2 copies of that, which leaves the plus 2 and the minus 2.
Yeah, so I guess I want something 1.
Oh, but then the next one is wrong. The next algorithm is wrong.
So apparently nobody learned Gram-Schmidt.
I can do it in equations, I can't do it in a matrix.
Well, you've got paper.
Yeah, right, okay, so I guess the major thing that's throwing everybody off is the fact that we're used to doing Gram-Schmidt working in the standard inner product and some weird list of the vectors.
Yes.
And now we're doing it the other way around. We have a non-standard inner product, it's right here. And we have just a perfectly ordinary list of vectors, I guess. So, you know, just these basic vectors over here. So, that must be what's throwing us off, but I think it shouldn't throw us off. I think you should still be able to use the mechanics of the algorithm, essentially the same one. So I'm thinking that x, comma y, comma 1, 0, 0. I want the inner product of that with the other things. Yes. Be 0. Where's the alpha go? And I also want.
Is it with that or is it 1, 1, 1, 1?
So you want your third new basis element to be orthogonal to your first new basis element, which happens to be the same as your.
Well, I guess I'm just trying to solve for x and y here.
I don't agree with the second equation. The second equation should have a negative 1, 1, 0, because you're trying to figure out the third new basis element by requiring that it's orthogonal to all the other new basis elements.
Right.
And the second new basis element, as you see up there, is negative 1, 1, 0, 0.
Okay, but let me ask, is being orthogonal to the two old ones equivalent to being orthogonal to the two new ones?
I think it's better to write down what we know is right and then decide whether that's true.
Well, it's not many times. Am I making a mistake? I think that if you want to prove that you're orthogonal to a whole two-dimensional vector space, you can just prove that you're orthogonal to any vector.
Sure.
Okay.
Right.
I agree with the core of this method there.
Okay. And which one of these is something you can solve for first? Y first and then X, or X first and then I guess this seems like you can solve them separately, is that right?
I think solving for X is incredibly easy.
So solving for X gives you what? Should be easy.
Remember, it's a funky inner product, right? But
Oh, wait, but am I screwing up here? You're also saying this one?
No, that's.
Okay. I'm supposed to be using this. Okay, right. This is not that product. This is our funny product. Okay. So why is it easy to solve for X?
well, maybe it's not so easy. But go ahead and do it anyway. So what's the inner product of X and 1? Well,
That's
it's
still X,
X.
1. On that X. Are you sure that's not minus
I
1?
approach this kind of differently. Can I kind of say how I approach this?
Yes. You want to do it?
Over here, I only had labeled these with like letters, like capital A through E or something over here. So that and I know that, so I can say that A dot E is the entry here, you know, based on the dot.
Okay.
So then I came over here, and we also know this dot product, our dot product is community, where it's captured. So then I come over here and label these new things like A star, B star, C star, whatever. And then I can just write equations for it, and it seemed to work out as I got those numbers before we did just algebraically.
Yes,
Are these the numbers that you actually?
Yeah, I got 1 minus 2 out of that, yeah.
Okay, so, yeah, let me just check these numbers. So we're saying 1, -2, 1, and 1. So 1, -2, and 1. So 1, -2, 1 times this, -2 times this, 1 times this
Yes.
is 0. Okay. And I just actually check this as well. 1, -2, and 1. And that should be
1, that should be, no. That should not be 1. No, but you see the second row and the second row, they don't. No, they do.
So, can I like do it? What's wrong with using algebra?
Yeah, algebra is fine.
Okay,
We are not used to these figures, that's all. We don't write them equations.
Okay, so what's the inner product of this guy and this guy? Let's try to figure it out. So what's the inner product of the first old one with the first old one?
That's
1, but x times it gives x. What's the inner product of the second old one with the first old one?
2y.
1, 2, so 2y. What's the inner product of the third old one with the first old one? 1, and I get 1. That better be 0.
But is the camera pointing to?
Yeah.
Oh, backwards.
And how about for this? So what's the inner product of the first old one with the second old one?
1.
1. So you get an x, right?
Plus
What's the inner product of the second old one with the second old one? 2.
Wait, the first one is wrong. The first one is x plus y plus 1. The first equation does not have a 2 in it.
Okay, I asked you what's the inner product of the second old one with the first old one?
It's 1.
So it's 1. And then the inner product of the third old one with the second old one?
2.
2. Okay, so both of those have to be 0. Okay, I'll let you do the rest.
Y equals -1.
And then comes with that next thing.
0. 0, -1.
So which way should we go? Are we going this way or are we going this way?
No, the one above.
Let's fill it up. Don't
This
use
is
it.
multiplied by 0.
Oh, we need to do this right here?
No.
Okay, so what is it?
1 is 0.
Okay.
The next one is -1.
Yeah, I think that looks more clean.
That works.
Yeah.
Yes, that does work.
Okay. Now we're doing the next one? All right, and we have a method, or we will try our own method, see what we get.
No, it's just that x plus y plus z is 0, x plus 2y plus 2z is 0, and x plus 2y plus 3z is 0.
Why don't you go up there and do it?
I hope for that, right?
So you're doing it the way I was doing it?
Yes.
Yeah, okay. There are lots of ways to do it, I'm sure, but
It's done.
let somebody dive in there and do it.
So now you want to do this as well. This is a black pen with a red pen with a black cap. So there's a black pen with a red cap. And this time, what do you want to say?
We have a V1, and it has 30.
And then the equation is healed. Now I can do this much faster because we have seen this once already, so I can write it off. So I'll just remove the equal to 0 part.
Okay.
And the next one is were all 0 and solve 3 equations in 3 variables.
Okay, so there should be one that's like easier to solve first.
These two together subtract, so z is negative 1.
So we're getting negative 1 there.
Yeah.
Okay.
And remove one equation. And here 2, so z is negative 1, so and you also, if you subtract this from that, you get y plus 1, so y is negative 1. That removes 1 more information, x is 1.
Now let's try the next one.
Yes.
So x, y, z, and w.
And 1.
I'm used to doing it some other way, which I'm having trouble reconstructing on the spot, so just try to follow everybody else. And now we're just trying to sort of write these,
Yeah, you
write these out in terms of the,
take the coefficients based on the rows up there, based on the rows in your matrix.
okay,
So the first one would be z plus y plus x plus 5 equals w plus 1.
say again?
You probably want to do it on this board.
Yeah.
The next board, yeah.
Okay,
We have not.
So you just, so we're comparing it to the first element, so the coefficients are going to be all one with x plus y plus z plus w plus 1.
plus y, plus z,
Plus
what?
w, plus w, plus 1
Yeah.
equals 0.
Okay.
So the next one, we're going to take the second row of our matrix. It'll be
Okay.
x plus 2y plus 2z plus 3w plus 4.
Okay.
Could you write in black so our poor helpless viewers can see it?
Okay.
We start the bit of
Red cat?
Start a bit of over, so 5 equations.
Up here?
Yeah. Only 4.
The next one is
1, 2, 3, 4, 6.
So x plus 2y plus 3z plus 4w plus 7. And then one is x plus 3y plus 4z plus 7w plus 12.
And one more, or that's it?
No, 4 equations.
Okay. And we should try and talk to this one first. So like that's the easy way to do it. We'll try to solve for W first, is that right?
7 doesn't seem to work.
You should.
This one you want to add the first and the third equation, subtract from the 4.
No easy way to do it.
Two w minus x. I mean, yeah, you get some other stuff.
And you're gonna, it's not, it's probably gonna take a few minutes, but it doesn't come, it's not as easy as the last one. We don't get one of the variables just by adding to equation with the last one. It's
Okay.
very simplified stuff.
But the reason why it's being obnoxious is that
Yeah.
in the usual Gram-Schmidt method,
Yeah.
you sort of gradually switch over from your old basis to your new basis.
No, it is.
So that at every stage you have a different basis that you're working with, and you only need to do sort of one simple thing at a time.
But look at the fourth row. Multiply the equations by those coefficients and add them. The first 3 terms cancel out, all you get is w. 1 times the first equation, minus 1 times the second equation, plus 1 times the, minus 1 times the third equation,
Right.
plus 1 times the fourth equation, which is W.
Equals what?
Plus some.
W plus
Some
3,
constant.
W plus 3 equals 0.
Okay, so now you make it sound like if we had put 1 here or something, instead of, if we used the new base all along, that's what we here.
Yeah.
I think that's what you're saying. So I figured out,
Right.
Maybe that's.
Okay. So, okay, using that improvement, can you tell me the answers now for?
That's negative 3.
Negative 3.
Negative 3, yeah. Yeah.
Go. 7 plus 1 minus 7, 1. 13 minus 10, yeah.
Okay, and what about this one? What's it?
Well, at least let's do one thing. Let's replace the W's by negative 3 and just rewrite the equation. So remove the fourth equation altogether.
Yeah.
That data is useful. And just replace the W's by negative 3, so just change the constant. The first constant is minus 2.
I already solved it.
Oh,
Okay, good.
Excellent.
Okay, let's see this
I
there.
got x equals 1, y equals 0, z equals negative 1, w equals negative 1.
Say that again?
Negative 1.
Is that weird?
That might be right, I'm
I
not.
solved it,
What is that?
I just guessed that w was negative 1 and then.
What happened to the equation?
There is a way to check our answer, okay? So let's
Let's write down Alex's answer.
write down Alex's answer. What?
1, 0, negative 1, negative 1.
1, 0,
Negative 1.
negative 1?
Yeah.
And then negative 1.
Negative 1.
So you completely disagree with
I didn't actually get the check one.
I think he screwed up near the end of his calculation, which is, so we should use the
Yeah, I'm not trying to read
beginning of his
one to
calculation.
negative 1. So
No,
no,
if I go get my calculator, I have a program to solve that matrix really quick.
No. We use it.
Better than calculator.
I'm just saying.
So we can check it. 1 negative 1 negative.
What do you say, it's 1, 0, 1?
Alex, this row is not a problem report, so.
Oh.
So does that mean that it's all wrong, or? Part of it?
I mean, we don't know the numbers. Yes, that has to be negative 3. Though. We just solve
That negative 3 was accurate.
Negative 3.
You can just remove the other 3 numbers. So what the suggestion is you should replace the W's by negative 3.
And so change all the
Change
constants.
W plus 1 to minus 2.
From
Zero W is negative 3. Change W plus 1 to minus 2 in the first equation. And the constant.
And minus 2.
Minus 2. The next one is minus 5.
Got to check in.
The next one is minus 6.
Okay.
So add or subtract the third equation, second equation.
Now look at the third row and use those coefficients again. So subtract the second equation from the third. 0 minus 1, 1.
Okay.
So you get Z equals 3 minus 3. You get Z minus 1 equals 0, so Z equals 1.
Okay.
And then you want to, again, put those back.
Z equals 1?
Yeah.
Minus 1?
Minus 3.
And you can, this third equation.
And then here remove that, and now subtract. So Y equals 2.
Y equals 2. Okay.
And X equals minus 1.
X equals minus 1? Okay. Okay. And,
Now that we can check that it's orthogonal.
yeah, so.
Yes, it's orthogonal.
Okay, okay. Now, So this is the change of basis matrix, hopefully, if I just go up again, from the old matrix, from the old basis to the new basis. So it's a lower triangular matrix. Can you tell me about what the inverse change of basis matrix will look like?
Triangular. Upper triangular, same diagonals.
Well, I guess whether or not it's upper triangular or lower triangular depends on how you draw it. Let me start trying to draw it. So I guess I'll put I should put the new, should I put new on top and old over here, or vice versa. I'll put it like this, I guess. Not sure which is the best way to do it. But certainly, okay, so we have the idea that it would be triangular, but is it upper triangular or lower triangular from this point of view?
It should be lower triangular. Because now when you multiply them, you're doing multiplication, matrix multiplication using standard conventions. And standard conventions has the upper triangular matrices being grouped.
But moreover, isn't it true when you're saying matrix algebra, like the inverse of an upper triangular matrix, another upper triangular matrix?
That's what I was saying,
Yeah.
in a fancy aspect.
If you're doing this, you are converting from new to old to old, and you want to do that identity. So yeah.
So, okay, so it'll be lower triangular again. What other kinds of properties will it have? This change of basis matrix, before we calculate it.
Unipotent.
What is unipotent? This is unipotent as well? Because it's the identity plus strictly lower triangular, that's what a unipotent matrix is? Okay, are there any other nice properties that this has that the inverse will also have?
So I'm just saying unipotent, but that's a fancy way of saying it has ones down the diagonal.
Say it again?
It has ones down the diagonal.
Right, we already said that.
And zeros above.
Okay, well, draw the yeah, depending on whether you understand.
It's also got like, this one has integer entries, right? Like mentioned that.
Oh, okay, sure. That too, it would have the
And what about this one that we're going to have here?
Yes,
Anything nicer than that?
positive.
So it's positive. It's natural numbers, matrix of natural numbers. And it's clear why this one will be a matrix of natural numbers.
So there's a simple modules.
Yeah, we're expressing each one of these complicated modules as a mixture of simple modules. And it's just a real mixture. It's not even a mixture, an actual direct sum, which has been decategorified into addition of natural numbers. Over here, we have negative numbers, which if you think about their decategorified interpretation, they're kind of weird. Like these negative numbers over here are telling us about some sort of, negative objects in our category or something like that. Or maybe they're just formal things that don't really stand for anything. It's hard to tell at this point. But over here, the numbers in this matrix will really be meaningful in a categorified way. So, I guess we could try and convert the matrix in my head, I guess. So let's see. How do I say this? I guess, yeah, I'm trying to express the old ones as combinations of the new ones. I think it's like that. Right. And then I'm getting one? No, exactly right. Let's see. And one here.
So why did you get that last one?
Yeah.
Well, I'm just in my head. I'm thinking that if I add this and this and this, I'll get just a single one here. I'll get the.
If you want to do the ijth entry, you print the ith row in the jth column or whatever, and that's how you get it. So then the last entry was in the third row and the first column. And what it's going to amount to is multiplying this third row and that first column with a 0.
So which one are you talking about?
The one that we last taken.
The one here?
Yes.
And did I do it correct?
Yes.
Okay, good.
And all I'm saying is, yes, to do that, to do the first one now, to do the 4th 3 entry, which is what you want to do.
Yeah.
Multiply the 4th row here with the 3th column there. And you're supposed to get 0. That
Let
means.
me do it my way and let's check if it's the same answer.
Okay.
So I can
I
create
hope
a
it's the same.
1 here, am I? No? This is what?
Oh, the 4th one is 3th column. Yeah, 1. Sorry. I was looking at the different column.
Okay. Okay. So far I've added this one and this one together, and I keep getting, 1, 0, -2, 1, but, so maybe I need a 2 there.
4th row and 2nd column. Yes, the 2.
So I'm getting 1, 1, 2. Okay, so I'm getting 1, 0, 0, and then 1, 1, 2. I'm getting -1 here so far. So I think I need 1.
Yes.
Okay. And now I'm trying to do this one. And I'm just not very good at reading algebra the way it's usually done. I'll just try and act it out the way I'm thinking about it in my head. So I've got this one, and now I'm trying to add some copies of this one to it to get 0 here. So I better add 3 copies there, I think. So I've got 1 and 3, and that gives me -2 so far. So I better have 2 there. And now I've got 4. Yeah, I'm trying to get 1, 0, 0, 0. I've got 1, 3, 2. Okay, so 1 of these, that's 2. 3 of these, that's a total of -1 so far. 2 of these, that's a total of -3 so far. And 3 of those. And you can work the last one out. Last one is very easy, because that's what you want. So, does this bottom row look very familiar to anyone? What's it saying? It's telling us the multiplicities in this representation of, it's telling us the multiplicities in this representation, the old flag representation, of the new irreducible representation. These numbers look at all familiar to anybody? These are I thought I might recognize these as the dimensions of the irreducible representation. And there's some kind of fact that well, yeah, but then in particular that the irreducibles appear with a multiplicity equal to their dimension. In the
Did you ever get people to work out the dimensions of these irreducibles, or?
we can do that right now. So we should be able to get these matrices, and they could easily be able to tell us the dimensions of the irreducible representation, because we know the dimensions of the flag representation. So tell me the dimensions of the flag representation. The flag representations are the old representations. So what's the dimension of a flag representation? You just count the number of flags. So this is a one-dimensional representation. 4, 6, 12, and 24. And So what do we do? I guess you could feed these numbers into this matrix, is that right? And they'll tell you the dimensions of the new representation. So this new representation will be, yeah, right. So I guess I'm going to be in 1, 4, 6, 12, 24.
Multiplying this by that column vector.
Yeah. So out here I'm getting 1. Here I'm getting 4 minus 1 is 3. Here I'm getting 6 minus 4 is 2. Here I'm getting 12 minus 6 minus 4 plus 1 is what? 3. And here I'm
24.
I have to know, that's why I'm going to work out B1. So, and again, and I'm going to be matching the numbers that we got here. But the reason is because this theorem that says, so this is actually the regular representation of the permutation group. And we're saying that the irreducibles appear in the regular representation with multiplicity equal to their dimension, which I guess is interesting. So right. So I didn't do that good a job of showing you how easily and quick this can be done, but it can be done very easily. This is a sort of decategorified way of thinking. And later, we really want to see the advantages of the more categorified way of thinking. So, like, what am I trying to say?
There's one thing as well.
Yeah.
If we actually got the matrices, it proves that what we started with all the way to the until now we had no proof of the fact that the flag were reduced from a base. But since the Gram-Schmidt does yield the basis,
I guess, yeah. Yeah, I was appealing at one point to some theorem that says that the number of times is flat. Calculate. Oh, I see. You want to be linearly independent, right? Okay, yes.
But it is because
Right. So this, yeah, it's not really that way. That's right. That's right. I guess that's also just equivalent to taking this matrix and somehow calculating it as what, non-degenerate in some sense. Yeah. So yeah, so we do want to work towards making this very decategorified calculation into something much more categorified. And I guess maybe we can make some steps in that direction today. So, yeah, I guess what we'll try today is we'll make some very baby steps toward making this decategorified calculation more categorified. And specifically, one of the things you can do is sort of a categorification process is when you see a number that maybe you just think of as the dimension of a vector space or the cardinality of a set, you can sort of categorify it by actually identifying what the elements of that set are. And that's what we can do starting over here. We have this matrix of natural numbers, and we did actually got these numbers by briefly at least considering the individual elements of these sets as actual individual elements of a set. But we kind of skipped over it very quickly, and we just wrote down our results. So I just write down the number of things that we found. And you know, just writing down the number of things that we found, that's a way of expressing your lack of interest in the thing itself. You know, say like, oh, there's 10 billion people, I don't care about any of them. And so one of the things that we can do to sort of regain, to express our actual interest in understanding the individual elements of, this 7-element set, this 4-element set, etc., is we can develop notation for describing the elements of these sets. And that's what we're trying to do right now. Develop some convenient and perhaps suggestive notation for describing the elements of these sets. And remember, the elements of these sets are certain geometric relationships between geometric objects at certain times. And there are a number of different convenient and suggestive forms of notation to use. And I think John has already implicitly or explicitly introduced some of them. And so we'll meet up with some of the notation that John has already introduced today at some point. But let me try to see some notation now. So I guess I also want to, before we start writing down this notation, I want to make one more comment about what we're doing here. I want to comment on the fact that we're doing some calculations, and all our calculations are directed towards understanding, allegedly directed towards understanding the representation theory of one particular group, the group whose name I give as 4-bag. But secretly, the calculations that we're doing have significantly wider applications. They don't just apply to this one single group. And the reason that there are other groups that they apply to. They apply to groups like GL or F. GL4F for lots of different fields. And, or perhaps I could also say, maybe I could say PGL4F. So GL is the general linear group. It's the automorphism group of a 4-dimensional vector space over the field F. PGL is called a notation for the projective general linear group. So this is a certain quotient group of this. These are very closely related groups. You can kind of think of this as the automorphism group of a 4-dimensional vector space. You can think of this as the automorphism group of the associated projector space. That's why it says projector here, P. And the point I'm trying to make is that all of these numbers that we calculated here, when we calculated them, we were thinking of it as having to do with the group 4-bag. We were thinking about how to compare, how flags can relate to each other in the geometry of this group. But we've also talked a certain amount about how a lot of the rules about how the geometry works of the flag works the same way for these groups as well as for this group. And we need to talk about how you can think of this group here as being in some mysterious way a special case of, I'm not quite sure whether it's a special case of this group or of this group, or sometimes what? We sometimes talk about this imaginary field F sub 1, the field of one element, an imaginary construct that people sometimes try to give real meaning to. But sometimes they don't try to give real meaning to it. We just say that, there are all these Q multinomial formulas and things like that. And that when you plug in the value Q equals 1, you get certain answers which tell you about what happens with this group instead of about what happens with these groups. So that's a comment I want to make, that we're doing some calculations here. We start out thinking that we're just doing calculations applying to the representation theory of distances. But we're actually doing some calculations. We change the base matrices that we calculated, telling us about the multiplicity of some irreducible representation and some more complicated representation. These calculations have an application to the representation theory of these other groups as well. So they're better calculations, they're more useful calculations than you might at first thought they were. But now I'm going ahead and going to tell us about a system of notation for the names of the sets whose cardinalities that are written down in this matrix here. And developing the system of notation is a bit of work towards categorifying the calculations of the here. So here goes. I'm going to do this example right here. Somehow this 7, oh, these are always nice, simple numbers. They're all like very, I don't know, nice. The 7 should not get sore thumbs for some reason.
7 divided by 4.
7 divided by 4, yeah. So just, it seems like a nice generic example. And I'm going to show you a system of notation to describe these 7 different things. So here goes. So first of all, notice what this 7, notice where it is in the matrix. It's this entry right here. So this Young diagram and that Young diagram again. And so this Young diagram has 3 rows. And the sizes of these 3 rows in this Young diagram are 2, 1, 1. And I'm going to write that down here. 2, 1, 1. And now I'm going to try to find all of the matrices of natural numbers that look like this, where these numbers here are the column sums, and these numbers here are the row sums. And that will actually be a system of notation that describes these 7 things. So, can anybody think of it? Can anybody think of a matrix of natural numbers here?
So that was
You're supposed to find a matrix of natural numbers so that these are the rows, the column sums. 2, column sum here is 2, and the column sums here, sorry, the row sums here to be given like this.
So first row, 1, 1, 0.
1, 1, 0.
1, 0, 0.
1, 0, 0.
0, 0, 1.
That works? Yeah, I think that gets the right row sums and then correct row sums and correct column sums. That's an example of it. Let's find as many of these as we can. Okay. Right. The same thing except switch the second and third row. I think it looks like that. Does it do it?
The first row is completely different now.
I mean, that's it. I mean, that's true, isn't it? I mean, that's
Maybe I didn't say it right. I want to say we're switching.
You're using row as a synonym for column?
I guess, okay.
That's okay.
Okay, no, I'm sorry, yeah, okay.
But that is one.
Yeah, that's fine too.
Okay, yeah, but I just never what you said.
One, 1, 0.
Okay, let me try to do literally what you said. Switch the second
Second and
row.
third row.
Okay.
So
1, 0, 0. 0, 1.
The first row should stay the same.
the first row, that's fine. That's what
These aren't rows?
No, those are columns.
Oh,
Columns. So
That's
these
okay. And then-
columns hold up a building
Now
reverse.
we do the other. Now switch it the other way. So 1, 1, 0 on the first. That's zero. Yes. Now do 0, 0, 1 across. And then 1, 0, 0.
Okay.
We got two other ones out of that process. So-
Sure, yeah, I was ready to.
I wasn't trying to do that. I was trying to.
Yes, sir, there are exactly 7 of these considerations.
I've done it so many times. I mean, I'm trying not to cheat here. I'm pretty sure there are 7. After we think of 7, try and think of another one, and you shouldn't be able to think of another one.
How about
What's the next one? Not yet.
All is there 1 there, so 1, 1, 0, 1, 1. And then, 1, 0, 0, 1, 0, 0. 1, 0, 0 again.
One more? I got it. Okay. So, you got any others?
Can you have a 2 in the upper
Oh,
corner?
2, 1, 1 diagonal, everything 0.
Any others?
Switch the the diagonal to the anti-diagonal for those ones.
You believe that there aren't any others?
Yes.
Class is almost over, there's better not. We'll just humor the teacher.
Sure. Right. So, okay, now remember what this young diagram is, 2, 1, 1. Well, again, what do these things stand for?
Non-degenerate.
Non-degenerate ordered pairs, right? So these are alleged to be names for the ways that two non-degenerate ordered pairs can relate to each other. Now, to give sort of wordier description, so like if I give you, how about, let's do this one. Anybody give me a sort of verbal, wordy description of what this relationship is?
The same order pair, these are different order.
Yeah, exactly. Reversing the ordered pair. How about this one?
The exact same order.
This is reverse. This is
Equal.
exact same. Yeah, this is quality or whatever you call it. What is this one up here? What is that one? I guess that's as different as possible, don't it? Non-overlapping ordered pair?
So it's my leftovers are your ordered pair,
Yes.
Yeah.
or your leftovers are my ordered pair. The
But
first
then you
row and the first column is the leftovers, right? The two guys that aren't in the ordered pair. And then the next
Yes.
rows and columns.
I was going to say like no overlap or something like that. So-
Yeah.
Okay.
And, what's this one?
The first entry is the one, the same as the second entry is the other one.
Yeah, it's something like that. You get annoying.
And you kind of write an example of it, or I mean, how would you want to call that? You can say like, you have A, comma, B, and C, comma, A.
But you, okay, we've got 3 of these so far. Okay, I guess these are the 2 cases where there's an overlap of 2. This is the one case where there's an overlap of none. And all these others are the cases where there's an overlap of 1. So it's like,
What about that one right next to you?
this one right here. Maybe this is the same first one?
And one of the same.
Yeah, I think this is the same. I think this is the same first one.
Mhm.
This this is the same second one, and this is somebody's first one, somebody's second one, and this is somebody's second one, somebody's first one, or something like that. That's what I think it is. So, this is a system of notation that you can use for all of these things, because it's sort of one example here. So let's think for, I claim that this is a suggestive system of notation. Let's try and think a little bit about what I mean. What am I claiming that it's suggesting? I'm claiming that it's suggesting something for us. So we're representing these things by matrices. Matrices of numbers of a certain kind. And let's think more about what these things are. So these things are the 7 possible geometric relationships or logical relationships between a pair of flags of this particular kind. So these geometric relationships, we've also called those things, we've called them Hecke operators, because it turns out that those, there's this theorem that says that the geometric relationships between objects, between kinds of objects, give you these morphisms, these intertwining operators, these equivariant linear operators between permutation representations of groups. So we're saying that, that there's a certain space of intertwining operators that's a 7-dimensional space. So there's a basis for this Hom space that has 7 elements. So we're saying that these 7 things over here are operators of a certain sort. They're Hecke operators. We're saying that there's 7 Hecke operators. And this forming the basis of the Hom space between this representation and itself. There's forming the basis of that Hom space. There are 7 Hecke operators. And here we're representing those 7 Hecke operators by matrices. So what's suggestive about that? Say it again? Yeah, I guess. I mean, we know that. I mean, they started out being Hecke operators. By definition, they were these certain kinds of linear operators, intertwining linear operators between group representations. So yes, of course they were linear operators. So we're representing certain kinds of linear operators, namely Hecke operators, by matrices. And what's suggestive about that is that it should remind us of some other context where people represent linear operators of a certain kind by matrices of a certain kind. But it should be suggestive in a perverse way, because this reminds us of that, but it reminds us of it in the strangest possible way. It's like a completely different game we're playing here. It's very tricky to figure out what's the relationship between what we're doing here, which is representing certain kinds of linear operators, namely the Hecke operators, by matrices of a certain sort. It's tricky to figure out what the relationship of that is to the other thing that people do with matrices and linear operators, right? Right, that's what people do with linear operators. They represent them by matrices. They do it all day long, but in a different way.
In particular, this representation that we're talking about is not 3-dimensional, right? Am I right?
That's one thing that's perverse about it, right?
So we're describing operators from it to itself by matrices. So 3 by 3.
Yeah. So what we're doing here is a weird combination of the familiar and the strange. Familiar because we're representing linear operators by matrices, but it's strange because we're doing it in a way that seems completely different from the way that people normally do that. And we'll just kind of leave it there. That's a suggested mystery for what. There are very interesting relationships between those two different ways of representing some kind of linear operators by matrices. They're interesting relationships, but they're not to me, they're not obvious on the surface.